Hey, this is Dr. Berry. Let's chat for just a few minutes about... Nobody recognized that? Let's chat about this upcoming speaker. First of all, public service announcement. The Starbucks, which is right through this door, has real heavy cream and real butter, just in case you wanted to know that for your coffee. Okay. This speaker is an advocate for animal source food to improve metabolic and mental health. She offers a persuasive argument against the relative merits of a plant-based diet, especially with regard to dietary fiber, anti-nutrients, and toxins found in plant food. She makes a compelling point about the nutritional quality of animal versus plant-based protein and fat macronutrients in the human diet. Ladies and gentlemen, Amber O'Hearn.
Thank you. And thank you so much for inviting me to this conference. Oh, I don't have a clicker. Right here? I don't have a medical background. My background is in math and computing and cognitive science. But I became interested in medicine and metabolism because of personal experiences. So I suffered with major depression in my 20s, and then in my 30s I was re-diagnosed with bipolar disorder, which I then was able to put into complete remission using a very low-carb, meat-only, plant-free diet. And because of that, I became very interested in the role of meat in particular and ketosis in the brain and the health of the brain, and so that's what I'm going to be talking about today. So, one thing we know about the brain is that it's extremely energy intensive. That's just the nature of the tissue. Every tissue needs some energy to survive, but different kinds of tissue need different amounts of energy. The brain is one that needs a lot. Others that need a lot, for example, are the colon and certain organs like the kidney and liver. So the more brain that you have relative to your body, the more energy you're going to need to fuel it. Oops. One way to measure the proportion of your brain compared to your body is this encephalization quotient. It takes into account some other factors. This graph is a variety of hominids and where they come in the encephalization quotient. So we've just kind of lined them up. We have the gorilla down near about 1. Pongo is the orangutan. Pan is the chimpanzee. And then we have a line of pre-human ancestors, including the Homo genus. And as you can see, the Homo sapiens are this big jump above everything else. So over the course of a couple of million years, we actually tripled our brain size compared to the pre-human ancestors. And so now we're at a point where an adult human has so much brain relative to their body that we're actually using, out of all the energy that we create, about 20 to 25% of that is used in our brains. But if you think that adults are highly encephalized, look at children. So this is just a visual so you can see the proportion of the size of the head compared to the rest of the body. This one on the left is a half-year-old child, and so can you imagine if your brain took up like a third of your body, how much more energy that we would require? And so in neonates, more than half of the energy that they're generating is going to that brain. So where are they getting all this energy? Well, one of the other things that we have that's different from other mammals and other primates is not just a larger brain, but a larger fat mass. Humans are really fat. And I don't mean that in an insulting way. Even lean humans are really fat. So if you think of a lean adult male who's maybe around 12% fat, that's a chimpanzee male is less than 1% body fat. So that's the kind of difference that we're talking about. But a woman is even more fat, and a baby is even more fat than that. How fat is a human baby? Well, here these graphs are from a paper trying to explore different hypotheses for why babies are so incredibly fat, human babies in particular. And so this first graph on the left is comparing it shows the human on the left coming in at about 15% fat. And there's a variety of other mammals. The only other primate on that graph is a baboon at 3%. A chimpanzee comes in around 3% as well. Among the different hypotheses that they were exploring in this paper, none of them really seemed plausible except for the idea that we needed to have a source of energy to fuel these huge brains. So the other graph on the right here shows the amount of oxygen out of metabolism that's coming out of the brain, out of all the metabolism oxygen that's going on. In a human at birth is way up there at 60%, a human adult down at 20%, and for comparison, a chimpanzee is at 8.6%. So children and babies have larger brains and they have more fat, but they're also more ketogenic. In fact, until you're an adult, basically the ketogenic ability that you have is inversely proportional to how old you are. So you get into ketosis more easily, but also you take up ketones from the blood more easily. So this graph is from George Cahill, and what it's showing is the beta-hydroxybutyrate in the blood after a certain amount of time without food. You'll notice that newborns start out, they're already in ketosis. Newborns are always in ketosis. It's not like the level of ketosis you'd find in a therapeutic situation for epilepsy, for example, but it's already at about 0.5 millimoles, which is considered the nutritional ketosis range. And if you remember that children are more efficient than adults at using those millimoles, you could make an argument that that's something more like 1.5 or 2 even. Infants, they don't start in ketosis. That's probably because they're being fed cereal, but then it only takes a couple of hours before they're back up to that 0.5 level. And then as an adult, you'll see women are slightly better at it than men, but it takes about a day to get to that level. So why ketones? We've got this brain that's being fueled by the fat, but it turns out that fat doesn't cross the blood-brain barrier very well, and ketones do. So the ketones are kind of a transport form to get that fat energy across the blood-brain barrier. We actually know a lot more than we did about the role of ketones in the infant brain in recent years. This is a table that summarizes some of the data of some of the different studies that have been done. So for example, in the top line, we know that even in gestation, about 30% of the energy that's going to the brain is coming from ketones. The placenta is full of ketones, and that's not even counting, the mother doesn't even have to be on a ketogenic diet. Who knows if it would be different if they were, if it would be more. And then once the child is born, they're getting about 50% of their brain energy needs met by ketones. And if you think about that, so you've got this 60% of all of the energy that they're creating is going to the brain, and then half of that is ketones. That's really a substantial amount. Why are infants in ketosis so easily? One of the reasons might be that the breast milk itself has medium chain fatty acids in it. And that's not just true of human infants. Many mammals have what you call ketosis of suckling, and that's probably because of the medium chain fatty acids that are there. And then in this third line, there's something else that's really interesting to me, and that's that we know that up to 90% of the fat and cholesterol that's in the brain is actually made out of ketones. So the brain's mostly fat and cholesterol, and fat doesn't get across the blood-brain barrier very well. So in practice, almost all of that fat and cholesterol is made in situ in the brain, and we know that that's actually done in practice by ketone bodies. So we also know the pathways. Here are 3 common pathways that have to do with ketosis. The first one is ketogenesis in the liver. And I'm just going to point out that there's an enzyme there called HMGCS2, and I'm going to briefly come back to that later. And we have the pathway B for oxidation. And then there's this lesser talked about pathway C, which has two branches, one for de novo lipogenesis and one for cholesterol synthesis, and that's how that happens. So I like to think of ketones as this transport form with respect to the brain of fat to get that energy and material across into the brain. What else is transported? Well, there is a kind of fat that does cross the blood-brain barrier very well, and those are the long-chain polyunsaturated fatty acids, arachidonic acid, which is the omega-6 in the solid line here, and DHA, which is the omega-3. This graph is showing the amount of incorporation into the brain just before and after birth. It's really very significant, very important, because all of the phospholipids contain this, and your brain wouldn't work properly without them. So, in a sense, the fat and the ketosis has multiple functions. Not only are we getting the fuel out of that fat and taking it to the brain, we're getting substrate to make fat and cholesterol for the brain, and we're delivering these important fatty acids for phospholipids. And all of this has to do with the growth period of the brain. But another thing that's unique in humans is an extended brain growth period. So most mammals, all other mammals that we know of, by the time they are weaned, their brain has already stopped growing. So for example, we have the chimpanzee up at the top here. They have this ketosis of suckling, and that goes on, but the brain growth has basically leveled off long before the weaning occurs. But in humans, that's not the case at all. Our brain growth is still growing like a fetus long after we've already been born, and then it continues past weaning. And so humans are unique in a lot of different ways, but this brain growth that continues ongoing is one of the more spectacular ones in my view. All right, so it would be really nice if we knew more about the did I skip a slide? No, okay. About the ketogenic ability in other primates, but we do have some comparisons with some other species. You might think that a dog would be in ketosis, right? A dog eats a low-carb diet. But in fact, if you want to get a dog into ketosis, you have to either deprive them of calories or put them through some intense exercise or deprive them of protein, or you could give them MCT oils and that would work too. But even if you completely fast a dog, it takes longer for a dog to get into ketosis, so they're even further along on that chart. And they never get to the deepest levels that a human would get into. The rodent is the best model that we have for studying ketosis in non-human animals, and we're very fortunate in that you can actually get a rodent into ketosis without calorie restriction and without inadequate protein, but just barely. If you give them even just a tiny bit more than the amount of protein they need for nitrogen balance, they'll go out of ketosis immediately. This makes research very tricky. And it's a contrast to humans, because humans, as you know, if you're on a ketogenic diet, you don't have to stick to the exact minimum. Maybe more protein is going to lower your ketosis, but you can actually eat maybe 1.5 to 2 times as much protein as you need to stay in balance, and you're still going to be in way more ketosis than any of those other animals. One other animal that I have looked at and I didn't represent on this slide is the dolphin. Dolphin I thought would be interesting because they have, not only do they eat a low-carb diet and go for long periods between meals, but they also have really large brains like us. And I found that they actually didn't go into ketosis either, which was kind of surprising to me. I just learned a few days ago that many animals have a genetic loss of that enzyme, the ability to make that enzyme HMGCS2, and so that explains that mystery. Okay, another difference between humans and other species is their gut, and this is specifically a comparison among primates. This graph, I forgot to label, it's from Catherine Milton, and it's comparing just the relative proportion by volume of different areas of the gut. So we have the stomach, the small intestines, the cecum, and the colon. Well, if you notice, the colon is drastically reduced in humans, and the cecum as well, compared to our closest relatives, the chimpanzee and the gorilla. This was brought to my attention when I started reading about the brain, because there is a hypothesis called the expensive tissue hypothesis. Aiello and Wheeler in the 1990s were trying to explain the fact that we have great big brains that we know require a lot of energy, but we don't actually expend a lot more energy. We don't have a basal metabolic rate that's as high as you might expect given all this extra energy load. And they noticed that one of the other expensive tissues that we have, the colon, is drastically reduced. And so they said, well, maybe what happened is that we reduced our colons in order to give us the ability to grow another expensive tissue, the brain. But what did we give up when we gave up that colon? The diagram up here shows a skeleton of the torso of a chimpanzee and a human and an Australopithecus pre-human ancestor. And the point of the diagram is to show that the Australopithecus has this flared out skeleton, which leads us to believe that they also had room for a great big colon, the way that the chimpanzee and gorillas do. And what those animals are doing in their colon is kind of magic, because what they're doing is they're taking fiber, which no mammal can digest, and they're giving it a place where they're holding a factory full of microbes that each have one of these spinning wheels and spins out this gold of fatty acids. So all these animals are on a high-fat diet in practical terms, because they're putting something into their body that they can't digest and getting out fatty acids. So, what about our pre-human ancestors, the Homo genus, while we were developing our brains? Where were we getting our energy? If we had a reduced ability to spin fiber into fat, we still needed to get our energy from somewhere. A lot of people presume that we did it the same way that most of us do it today, using digestible carbohydrates. After all, there were some tubers available. But I'm going to explain why most researchers don't think that idea is tenable. So what else does a brain need? A brain is growing, and it needs energy, but it also needs a whole lot of nutrients. Amy mentioned some of them. And if you don't get those nutrients while your brain is growing, very often you'll have a deficit that persists, and you can't make it up later. In fact, the brain often grows in stages. So if you can't properly complete one of those stages, and then your brain just has to move on and start making the next thing, and you're never really going to make up for the fact that the previous stages weren't done correctly. If you think about the evolution of an organism and an organ that requires something, it makes no sense to imagine that you could have acquired a need for a nutrient, a persistent need for a nutrient across your development that wasn't available in your environment all the time that you were developing or making that evolutionary adaptation, right? So if there's some gap in our history where these nutrients that we needed to grow a brain weren't available, there's no way the species would have continued to develop that adaptation. It just wouldn't have happened. It wouldn't have gone forward. So we might not have needed them on a daily basis, but I think maybe there are nutrients that you probably would need at least weekly, week after week, month after month, year upon year, generation upon generation, for these brains to have developed the way they did. So what kind of nutrients are we talking about? Well, we've already talked about energy and some specific fatty acids, but there are many minerals, there are vitamins, and there are bioactive compounds that we need in order to grow a brain that are critical. Every one of these would cause a deficit, either cognitively or sensory motor deficits, that would not develop a proper brain. I don't have time to talk about each one of these, but I'm going to choose two to illustrate something. One of them that I'm choosing is iron. The reason I'm choosing it is because even today, in places that are less economically fortunate, that we know they have deficiencies in iron, and so we can see what happens. And what happens are deficits in cognitive function, motor function, social emotional function. So we're talking about temperament, we're talking about actual neurotransmitters. It's a big problem. There are two sources of iron, two different kinds. You can get them from animal foods or you can get them from plant foods. The best sources in animal foods are liver and red meat, shellfish, and you can get them from fish and poultry too. The plant sources are the best sources. Not all green leafy vegetables, but spinach in particular is high in iron, and then legumes and nuts and seeds. And you can enhance the absorption of the non-heme iron by taking something that contains vitamin C at the same time. However, non-heme iron is also inhibited by oxalates, and it is maybe ironic that the oxalates are very high in the very same foods that are high in iron. So it's not actually a coincidence. The iron that's in those plant foods has to be bound with something, and it's often bound with oxalates. The problem is when you put it in your body, it stays bound, and so it becomes very hard to digest it and to absorb everything that you're getting. So if you're looking at a database and it says, oh, spinach has this much iron in it, you have to take that with a grain of salt because it's not telling you how much iron you can actually get out of the spinach. The other example I wanted to bring up is arachidonic acid, and I'm bringing it up because it is DHA's ugly stepsister because it's an omega-6 fatty acid, which are sometimes considered to be bad, but it's actually very important. It's at least as important as DHA. It's important in just about every function. It's in the phospholipids, not just in the brain, but in your muscles. And if you look at the list of the kinds of roles that it's playing, you'll see that memory is an important one because of its role in long-term potentiation and hippocampal plasticity. Now, you can get that in any animal food. It's even in the muscle tissue. And you can't get any in plant foods. You can get a precursor, linoleic acid, but unfortunately, the conversion of that is very limited. It's not sufficient. We know that because if you compare formula-fed infants whose formula doesn't contain arachidonic acid but does contain linoleic acid, they will not attain the levels of arachidonic acid that breastfed infants will. So what did we have available? We're talking about the African grasslands. My 9-year-old came home last week and he said, Mom, do you know what the most important plant in the history of people is? And the answer that he gave me was grass, because, yes. But he was taught at school that the importance of grass was that it outcompeted the trees and pushed them further apart, thereby opening up a niche for organisms that had better mobility, thus making room for our bipedalism to compete. What they didn't teach him was that the other important part about grass is that it also opened up a niche for grazing animals. And I'm sure Peter will tell you a lot more about this. But that gave us and other animals access to a much higher quality nutrition as predators than we would ever get from leaves and fibrous fruits. So we had those in the form of ruminants, and they were megafauna, so they were really big, and that means that their proportion of fat was also bigger, because in mammals, the larger you get, the more proportion of fat you carry. And there was access to freshwater fish. I probably should have put parentheses around that because it's considered to have been more available later in the Paleolithic. And we did have tubers, but they were mostly inedible. There were two kinds, like there are now. There's the radishy kind, which is mostly fiber, so you're not going to get a lot of energy from that. And then there's the starchy kind, which are also mostly fiber, but you can get some starch from them, but the problem is that it requires cooking to really release that starch, and the time that we're talking about precedes the evidence that we had any kind of widespread use of fire. So we may have been able to use them in a limited way. We had access to nuts, but they were seasonal, and there were some other wild plants that wouldn't have contributed so much energy. So this table is from Cordain, and he's playing a mix and match game where he says, here are the kinds of foods that were available. Here are just two of our needs. The energy and those fatty acids, DHA and arachidonic acid. How could we combine the foods that were available to us to be able to get everything that we need to grow a brain? And you can see if you look at the energy column on the left, that it would be very challenging to get a consistent level of energy that you needed without using either ruminant animals or nuts. But then if you're relying on nuts, there could be an argument made that you could combine nuts and fish and get your energy needs met and your arachidonic acid and DHA needs met. And there are some modern hunter-gatherers that do exactly that, but as I said before, this seems to have only been possible in a later period. Really, the only way with this menu of foods that you could consistently get everything that we need to grow a brain would be, well, the solution's all basically in one kind of animal. You take a ruminant and you eat the muscle for protein, you eat the marrow and the subcutaneous fat for energy, and you eat the brain for DHA and arachidonic acid. And that's all you need. And that would be available year round. It's not so much seasonal. And it's really a perfect solution, and it's probably the only plausible solution for this year after year, generation after generation evolutionary scenario. The cool thing about that is that it fits in with this other information that we already talked about with humans being extremely ketogenic compared to other species in the face of higher protein. So in order to have developed the ability to stay ketogenic even with a higher protein diet, it stands to reason that we must have had some evolutionary time in which we had an environment, a food environment, that had higher protein levels and very low carbohydrate levels. And so this fits very well into the biological and physiological evidence. Living here and now, we have many, many options. We have the technology. We have agriculture. We have developed the ability to grow grains and tubers that we can release a lot of energy from because we can cook. We have selectively bred many fruits so that they are higher in sugar content and lower in fiber content. And we even have the ability to create supplements. For example, we can get DHA from algae and truck it in to wherever you want to be and not eat meat. So it's absolutely possible to meet your energy needs and even arguably your nutrient needs with a diet that looks something like this, as long as it's carefully planned and well supplemented. I don't mind that kind of argument nearly as much as I mind the argument that this would be a better choice than eating a meat-based diet, which we were adapted on. And the idea that meat is inherently bad seems to fly in the face of all logic. Not only that, but many people think that ketosis is not a naturally evolved state. And this bothers me even more. Something that I see very often in the literature, even literature among scientists who are studying ketogenic metabolism and seem in all other regards to consider ketosis to be a healthy thing will often start their papers by saying, this paper is about ketosis. Ketosis is an adaptation for starvation. Well, yes, we do use ketosis when we're not eating, but that's not consistent to me with the evidence of what ketosis is for the human being. Ketosis is a growth state. Ketosis is where we're growing our brains. Ketosis is an adaptation for growing brains. It certainly isn't unnatural, and it certainly isn't stressful to the body. So I think that we should stop saying this. And so to say that meat is unhealthy, I think, is contrary to all of the evidence. Meat is the vehicle by which our brains were allowed to evolve, and it is the vehicle by which we were allowed to evolve ketosis, which is not only important in the maintenance of a healthy brain, it's not only an escape route if your glucose systems are down. This is the very energetic system and structural system that we use to grow our brains. Thank you.